Good morning. Today I want to continue talking about integer quantum Hall effect, and I will try to explain the plateaus. And for that I will have to start talking about first edges and edge states. So last time what we did was we just solved Landau problem. Under only B is equal to minus BZ. And we mentioned that classical or quantum that by itself does not explain the plateaus. And my goal today is first introduced on top of B, I want to introduce electric field. And I want to put first electric field, and later I want to put edges. I want to put the system in a finite geometry, which are going to tell us a lot about what we see in the experiment. And lastly, and most difficult one maybe we'll do in the second hour, is we are going to put disorder and impurities. I want to start with E is equal to 0 and at finite B and no edges. And I want to make a baby calculation for currents. So what we are going to assume from now on and in the rest of this chapter is going to be, so B is large, B is very large, and that means h bar omega, which is h bar EB over MC, is larger than any other scale. So we can forget about higher Landau levels. Then the problem will reduce to physics of single Landau level. And typically we call this lowest Landau level. It's the one we are going to consider. And wave function from last time, if you remember, of the lowest Landau level is going to be properly normalized Ly e to the I k y. So this is the plane wave part. This is pi L squared 1/4 e to the minus 1 over 2 L squared x minus xk squared. So in this equation, L is h bar over m omega is the length, harmonic oscillator length, which can also be written like h bar c over EB, and xk is equal to k L squared. And the corresponding energy for this lowest Landau level is going to be h bar omega over 2. Let me also write that E is equal to h bar omega over 2. So we want to calculate the current. So the current, quantum mechanical current, is given by expectation value of J of x is going to be equal to minus E over M psi k star. There is no Landau level because I'm just looking at a single Landau level for the moment. And whenever we need, we can also sum over all Landau levels. So x, y. So this is minus I h bar plus E over C A. So this is psi k of x, y. And here A, the vector potential in the Landau gauge, was taken to be 0 minus Bx 0. And to find the total currents, I need to sum over all I need to integrate. Okay, so I'm considering like a sample like this. Maybe I can do it in this center. So this side is Lx, this side is Ly, and there will be current in the longitudinal direction, which I'll call Ix, and there will be current in the transverse direction, which I will call Iy. Because these psi's are like Gaussians, right? Like Gaussian is like a localized wave function. It cannot conduct current. We can automatically say current along x direction is going to be 0 because of Gaussians. But the current in y direction may not be 0 because there are like these plane waves, and that's what I want to calculate. So I of y is equal to minus e over m. This is the normalization, 1 over Ly, 1 over pi L squared. So this is minus infinity. The sample is finite, but because of like these like strongly decaying Gaussians, I can extend the integration to infinity. Right? That's like a standard procedure. So this is going to be dx. So when I need to take the y component of this, and when the y component of this hits on this wave function, it's going to bring down an ik, and there's also minus I h bar, and they are going to combine that. And for the vector potential, the y component is going to come with minus bx. So I'll operate all these and then combine all the vectors. This is going to be minus I h bar ik plus e over c minus bx, and e to the I and e to the minus I, they are going to be 1, and what will remain is only the Gaussian. And this, okay, let me copy and manipulate. So this I, this is minus I, and I want to take this EB over C outside. So this is going to be minus minus plus E squared B over C, and this one is going to be minus, and this is going to be H bar C over EB, and this one is taken outside. And this, yes, that's what I'm trying to show. And this thing x minus k, and this quantity, so this is what we defined to be L squared, and this is so this inside here is going to be x minus k L squared, which is equal to x minus xk, and we are integrating from minus infinity to plus infinity. We can change the integral variable from x to x minus xk, and each integral is going to be centered there. So the Gaussian here is even. So this x minus k L squared is odd. Then the entire integral is going to be 0.
So it's topologically insulated?
Yes, there is no current either in x or y direction. At the moment that makes sense because there is only magnetic field. We didn't put anything to drive the currents. In a little bit, I'll first put electric field, and then I'll put the edges, and then see how this picture changes. So this is actually expected. Of course, this is kind of like at the long way to see that, but if you look at the energy dispersion, it's going to be h bar omega n plus a half, and v and k. If you take the derivative, there is no k, right? There is no velocity in the y direction. If there is no velocity, there is no current. So that was the no current in x or y directions. Okay, that's good because that's what should have been. Now we are going to add electric field along x direction. Turn on E field. And for electric field in the x direction, I'm going to put this potential V of x is going to be equal to plus EX. And so we have to add this to Hamiltonian and see how the spectrum changes. So h of k, the interesting part, was equal to p squared over 2m plus 1/2 m omega squared x minus xk squared plus EX. And what I want to do is, like, there's like x squared here, there's x here. I need to combine these two factors to get a new x squared and change the variable, and then try to put this in a form similar to this harmonic oscillator. So let me do it in a couple of steps. Just like no calculation, just rewrite. So I want to put minus xk here, and I want to put plus xk. And I want to put the parentheses here, like that. And for me to be able to do that, I need to here put 2 over m omega squared. And lastly, I need to insert, so there's like something squared plus 2 times something else, and I need to add e over m omega squared, so plus and minus of the same thing. Then this Hamiltonian is going to be px squared over 2m plus 1/2 m omega squared. Let me call this x minus xk prime squared. I'm going to define what xk prime is in a little bit. So there is 1/2 m omega squared minus this is going to be minus 1/2 m omega squared times this factor plus xk. And here we can read what xk is. Xk prime is xk minus this thing, e over m omega squared. I just shifted xk a little bit. E. Okay, good. And so this also, okay, you can see, let me write in 2 steps not to lose track of the calculation. So let me write this like this. This is squared, and this m omega squared is going to cancel one of these, so this is going to be like that. And so what I want to do here is, so I want to so you can see there's like xk prime here. I want to write this one also in terms of xk prime. So I'll just use this line. Xk, wherever I see xk, I'm going to write it like xk prime plus e over m omega squared. Then this is going to be xk prime plus e squared, right? There is like one e, another one here, so this is going to be m omega squared. Yes, right? And this one is minus, this one is plus. What I'll do is like I'll write plus here, and I'll erase this one. And this thing, so 1/2 e squared divided by m omega was equal to e squared b squared over m squared c squared. So cancel m, cancel e. So this turns out to be 1/2. There is only one m here, and let me define it like v bar squared. So this is what we called drift velocity previously, and this v bar is going to be c c times e over b. I think I didn't miss anything. Let me check. Yes, I think that's correct. At the end, the Hamiltonian turns out to be h, again the harmonic oscillator part, plus 1/2 m v bar squared and I have, I think, one more plus e xk prime. So this piece is the harmonic oscillator piece. That's also going to be h bar omega n plus 1/2. So this is e and k is what I'm going to write. So this is just a constant shift, 1/2 m v bar squared, and this is also like some guiding center dependent shift in energy, plus e, which comes from electric field, xk prime. So this first one is lambda level energy. So this one is going to be drift perpendicular to electric field, and this last one is going to be coming from the extra potential we put, and the picture is something like this. We have so this v of x, so this is x when we put like a linear potential, something like that. It's like increasing linearly, and there are like these Gaussians at different xk, and depending on the position of this guiding center, there is like a position dependent energy shift.
So how do we know it's perpendicular to E field?
Because it is what we calculated previously, like drift, right? This is E over B. So previously we set up the Newton's equation, and from the Newton equation, in the presence of E, B, and tau, and there was like a drift velocity, and this is exactly the same thing. I don't see it from here. I remember it from the earlier calculation. But since this is energy, it's the square, so it doesn't know about the direction. You are right. Yes. And now we need to calculate V, okay, the current in X direction is going to be 0 again, right? We just put a linear potential, but wave function didn't change in the X direction. In the X direction, we still have like strictly localized Gaussians, and strictly localized Gaussians are not going to give any current. Let me just write that. Ix is 0. Still, I don't even calculate that. I need to calculate Iy. And for that, I need to calculate Vy, and Vy is 1 over h bar del E and k del k. And from here, I see that there is no k dependence here, there is no k dependence here, there is only k dependence here. It's going to be E over h bar, and xk prime was equal to something plus kl squared, right? Here. This is the one I'm going to use. Not this one. This one. Yeah. This one. The second term is just a shift. The first term is xk, and xk was, I don't know if you remember, but it was like kl squared. And if you take the derivative of kl squared, k is gone. There will be just l squared here. And this thing is equal to E over h bar. L square is h bar over m omega, m EB over mc. Cancel m's, cancel e's, cancel h bar. This Vy also comes out to be c times E over B. This is also telling you that there's like a current in that direction. Now I want to calculate the current Iy. So let me first calculate it for one channel, or one state, and then I'm going to sum over all possible states. So Ix, let me call it I for one channel. It's going to be minus E over T. This is minus E over T is Ly divided by Vy, and this is going to be minus E over Ly times Vy. But Vy is equal to V bar, so I can just put that. And to find, okay, this is Iy total. Yeah, I messed up. So the Iy total is going to be sum over all these states. So let me write that. So since all states come with the same velocity, there is no k dependence. But I need to sum over first all lambda levels from 1 to the one which is occupied. The highest occupied, I will call it nu. And I need to sum over at each given lambda level. I need to sum all states. And this is k is equal to 1 to, and each lambda level has like n phi degeneracy times 1. So this piece is going to give us what we called n phi. And this piece is going to give us nu, and n phi was equal to b times a flux divided by hc over e. And at the end what we have is, and I want to write a is like lx ly. So I want to take lx to this side and write this like jy, because I'm going to write something like sigma xy here, and this is going to be I think I forgot v bar is here. I want to write it like something like this. This is going to be okay, y, so this is yx, this is ex. Right, this is what I want to write, and sigma yx turns out to be, there's like an overall sign, let's not worry about that, e over ly. So v is c e over b, so I have taken care of this, nu, and there is B Ly divided by HC over E, and there is I took the Lx, this Lx, I took it to this side to write it like current density rather than, because this relation knows about current density. So Ly's cancel, and B's cancel, and this C cancels this, and at the end this happens to be E squared over H nu. Oh, and E needs to be, E is here, right? I shouldn't write E twice. So this E, let me indicate it like this here. So this sigma yx. So this is as in quantum Hall plateaus. Good. So it looks like we explained quantum Hall effect, but it's not so quick. I mean, this is just like a baby calculation that's giving us the light at the end of the tunnel, but still we need to put edges, because system has edges. This is going to be easier. I'll do it probably in this hour, but also we need to put disorder. This order is much harder to understand, and without putting this calculation does not mean that we explained the quantum Hall plateau. Any questions? Okay, I think I have enough time to consider integer quantum Hall effect edges. So we want to put edges to the system, at least 2 edges, because we are going to put 2 leads on the quantum Hall bar. But like for simplicity, let's consider only one edge, which is going to teach us a lot about other edges. So I want to have this coordinate system, right? Like x, and suppose I put my edge, right? X is equal to 0, and here this is like, so this is infinite wall. So that means wave function has to vanish as soon as you enter this domain. So, so we have 2 possibilities. One possibility is like this waveguide center xk is much smaller than 0. That means the harmonic oscillator is going to be somewhere over here, and the corresponding wave function is going to be something like that. So in this case, this Gaussian is like exponentially decaying, is not going to see anything about this wall, right? The wall is far away. Whether there is like a wall here or not is not irrelevant for this Gaussian, and the corresponding energy will also not change. So then E and K is going to be h bar omega n plus a half, and n is equal to 0, 1, 2, dot. So basically no change. But in the second scenario, like if I put this guiding center right on the wall, I have to think about that too. So this thing, I bring it here and put it like that. In that case, the change is going to be maximal, and I cannot put that wave function here, right? Because wave function has to vanish here. And I don't like, typically what we need to do is just go write the differential equation and solve it. But the differential equation is the same differential equation. There's no change, right? This is the differential equation, or like the first one we wrote. So this is the differential equation. Right? There's like derivatives here, but the only change is boundary conditions. solutions are the same, boundary conditions are different, and what we need to do here is just take the solutions that satisfies the boundary condition. So I'll erase this one, and I am going to put this kind of solutions, right? And this is not the first level, but this is going to be the second level. Or I can also put something like that, right? As long as I'm 0, so and these are going to be odd eigenstates of harmonic oscillators. So what I'm trying to say is like the solutions are E and K are exactly the same, h bar omega n plus a half, because we don't need to solve the same equation. Its equation is the same.
Wave function?
Yes. So the
It should remain 0.
yes, here it is 0, right? So it is 0, and only the anti-symmetric wave functions have 0 at the wall. And symmetric ones, for example, this one does not satisfy the boundary condition, so I discard this solution. And what I'm trying to say is that I have the solutions by n, not 0, 1, 2 here. They'll be odd harmonic oscillator, 1, 3, 5, 7, and so on. Right? There's like a standard problem in Griffiths. You can think about that. There's like he is asking you to solve first harmonic oscillator in the chapter, and then in the exercise he's saying, what about half harmonic oscillator? You don't need to resolve it. It's just odd eigenvalues. Okay. It's a little confusing, but that's what it is, right?
But it doesn't vanish.
No, this one is vanishing, right? This wave function is odd. Odd wave functions are like x, right? Even is like e to the minus x squared. There's like so this is
It only vanish at the 0 point.
yes. After that, you don't care, right? You discard this, right? You are saying that I am only going to use the wave function on the left hand side. Once it satisfies the boundary condition, I don't care what happens here. I'll never go there anyways. But this one does not satisfy the boundary condition. I am like in the valid domain, and I don't satisfy the one, so I cannot take that wave function. So the picture is something like that. Let's now generalize this. So this is yeah, it is taking a little bit thinking to convince yourself, but this is like standard argument. Now I want to draw the eigenvalues exactly like I'm drawing the eigenfunctions. So if I'm deep inside the sample, I have all levels allowed. Right? This is n is equal to 0, 1, 2, and 3. So let me just shift this a little bit. But here I don't have all values allowed. Like I have, okay, let me just copy this and show which one I should discard. So I have exactly the same states, but I need to give up on this because this is not odd. I need to give up on this because this is not odd. I need to give up on that, and so on. And as the guiding center approaches the wall, so this state should continuously evolve to the state which is allowed, right? So it's going to go and do something like that. This one is going to go and do something like that. And this one is going to go and connect to the third one, and so on, right? So this is what we call bending at sample boundary. So we also do this a lot in, like, for example, energy bands. You take the energy band of bulk, and as you approach the edge of the sample, you just shift up or down depending on how the other side behaves. And our picture is something like that. So if this is for only one wall, if we have two walls, in the center we are going to have these lambda levels unchanged. but towards the end they are going to just bend like this. And same thing here. And it goes on like that, as many as you need. And another way of saying this, ENK is going to be h bar omega n plus a half plus, previously we had xk. I'm not going to put prime anymore because there's only one coordinate anyways, but in this case this term is going to be replaced with v of xk, right? That's the because xk is also following the potential anyways, and there can be small corrections which we don't care. The only relevant term is this one, and v and k is going to be 1 over h bar del e n k del k, and this is going to be 1 over h bar del v of x del x, and at x is equal to xk. And this thing is bigger than 0 if you are right side, and it's going to be, if you are here, derivative is negative here and positive here, and this derivative is going to be 0 on the left side. Let me try to calculate the currents and then finish it there. Like, let me first take only one such band. It's kind of like this, and I have to have a Fermi level, and everything below Fermi level is occupied. So this is E Fermi. Let me write it like mu Fermi. But what we do is like, so we apply a bias to sample, right? There's like a little bit shift on this side compared to this on this side. So let me write it like nu left, and this is nu right. Exactly like in the Landauer calculation in your book. So the current I, if you remember the Landauer calculation, was something like this. We had, so this is only for one channel, later we are going to sum over all channels. So first, sum over all allowed case, and each is going to contribute a T, and I need to look at the occupation of this level. And the T here, right, this is just standard current, Ly divided by Vk, and Vk is 1 over h bar del Ek del k. So then this is going to be minus E. So okay, this Ly, I am going to cancel with this Ly. And I'm going to write this like dk over 2 pi 1 over h bar del E k del k n of k. And in Landauer formalism, what we did is like we combine this, and we change the variables of integral from k to epsilon. And this bar and 2 pi are going to cancel. At the end we are going to have minus E over h. So this is dE, and this is going to be n of E. But there are two E's, one on the right hand side. I'm just copying that calculation, so we don't need to redo the calculation. It's going to epsilon minus nu right. This one comes with positive current here because of positive derivative, and the other one comes with minus n of epsilon nu left. And what we said there was like, okay, these n's are step functions in zero temperature, right? These are Fermi functions. This is going to be minus E over h, and step functions are just going to probe this exactly mu right minus mu left, just the difference, right? Whatever the energy difference here, that's the piece you need to get from the integral. And we said delta mu is the applied voltage, which is minus E times V. Let me not write it's actually Vx, but I don't need to write it Vx at the end. So we have I is equal to E squared over H times V, then sigma Yx is equal to E squared over H. So this is one channel. And if we have new channels, this sigma Yx is going to be E squared over H times nu. Right. So let me stop here. In the second hour, what I want to say is like first, so this is the sample H, and it seems like we have like a current here and current there, and this current is slightly bigger than this current. That's why there's like an overall current in the y direction. In the second hour, I want to start thinking about like impurities in the boundary. Why? So what happens if you put impurities? Like in the Landauer formula, we just put a T here, and we are going to discuss if we need to do the same thing in the quantum Hall bar. And also, I will also think about impurities there.
How do we say that right one is bigger than the left one? Because there is no extra tendency.
Because like this is the dispersion, right? And the dispersion, because of dispersion, I shifted the occupation here is just a little bit bigger than there. There's not enough, like there's a little bit, exactly like in the Landauer, right? You have quadratic form. If you don't apply any voltage bias, right movers are equal to left movers. But if you apply a bias, right mover is going to shift a little bit more up, and left mover is going to shift a little bit down, and the difference is going to be the current. But the difference here is these right movers and left movers are up movers and down movers. They are like separated. They are in the far ends of the sample. One is on the right hand side, the other is on the left hand. In the Landauer case, it's like on the same wire. Okay, let's take a break and continue in 10 minutes.